Okay, all right. Yeah, good afternoon, friends. Hey, actually, yeah, good afternoon. Yeah, I'm back again. Yeah, this time I'm here for correlation and regression. Actually, I'm just introducing you to this. You will be interfaced with more correlation and regression analysis in during analysis or during the practicals and in other course units. Actually, I guess even in mathematical cone we had a say on correlation and regression, so I will be a bit faster. Yeah, I'll be a bit faster, and we'll do them practically. We'll do them practically, so I'll be a bit faster. Okay. So, starting, or let's start with talking about how we measure association between two quantitative variables. Quantitative, recall quantitative, we're talking about those variables whose characteristics can be quantified or can be measured in terms of numbers. We're talking about numbers or quantity. Okay, and we're saying an association exists between two variables if a particular value of one variable is more likely to occur with certain values of the other variable. That's when we say there's an association between variables. Okay, if a particular value of one variable is more likely to occur with certain values of the other variable, meaning there's a relationship. Okay, one variable or the values of one variable depend on those of another variable. We have an example there that for high levels of energy use, there's the carbon dioxide level in the atmosphere tend to be higher. Of course, I brought that carbon dioxide to remind us of those formulas. Yeah, some of us had forgotten about our chemistry and so on. I decided to bring out something to remind us. Okay, even those who did, if you didn't do sciences, you didn't do chemistry, you did history. Okay, under the Bourbon monarchy, Bourbon monarchy. Okay, under Metternich, under Napoleon, there's somewhere you talk about those formulas. If you can do, you reverse your books. Yeah, under the French Revolution, there's somewhere those formulas come in. Okay, all right. So I just brought those to remind us about the things we used to do in science, actually from primary, secondary. Yeah, from primary, secondary, and then secondary and O level. Okay. So here we are saying for higher energy use, does the carbon dioxide level in the atmosphere tend to be higher? If so, then there's an association between energy use and carbon dioxide. Here is the case here. Yeah, if there is a lot of energy use and that leads to the carbon dioxide level in the atmosphere to be higher, then we assume there is an association between energy use and carbon dioxide. And meaning the values of carbon dioxide are happening with the values of energy use. All right. So that was to introduce us. Then we talk about the correlation and regression. And so how can we explain the relationship between two quantitative variables? Graphically, we can construct a scatter plot. Numerically, we can calculate a correlation coefficient and a regression equation. Okay, so we are going to look at each of those in more details. Okay, correlation. Yeah, here we are. I started with the concentration on the Pearson correlation coefficient. Yeah, we have the Pearson and then we have the Spearman. All right, you can read more about when we use the Pearson and when we use the Spearman correlation. Okay, so the Pearson correlation coefficient R measures the strength and the direction of a straight line relationship. Yeah, with this we measure the strength and the direction. Strength and the direction. How strong is the relationship between two variables and what direction are they taking? Yeah, is the relationship positive or negative? Okay. And the strength of the relationship is determined by the closeness of the point to a straight line, The direction is determined by whether one variable generally increases or generally decreases when the other variable increases. We'll talk more about that when we talk about the positive and negative. The positive relationship, they're taking the same direction. When one increase, even the other one will increase. When one decrease, even the other one will decrease. Whereas for negative relationship, they take opposite directions. When one goes up, the other one reduces. Okay, so what you need to know is that the correlation coefficient has to be between -1 and 1. Okay, it's between -1 and 1. Okay, so a -1 or 1 indicates the perfect relationship. So if you get a 1, it's a perfect positive relationship. If it's a -1, it's a perfect negative relationship. Recall the sign will indicate the direction. If it's negative, it means the direction is negative. When one goes up, the other one goes down. If it's positive, it means there's a positive direction. When one goes up, even the other one will go up. If you get a correlation of 0, it means there's no relationship between there's no relationship between the variables. Recall the scale is -1 to 1. Together, for which 1 on either case is perfect relationship. It could be perfect negative or perfect positive. Alright, I'm rushing through this because we're just reminding ourselves of this. Okay, so we're going to have an example. Okay, we are going to have an example. I'll just run and take you through how to get it. Yeah, my main interest is in regression. Alright. Okay, so saying the following data was collected to the study relationship between the sale price Y and the total appraised value of land in Mkono. Yeah. So that's the formula I would use to calculate the correlation coefficient. Yeah, I will not concentrate a lot on this correlation. Yeah, I just put it to remind us. Alright, so if you're given a number, the key issue is to look out for those elements. After knowing that I is equivalent to n into the summation of xy minus x into the summation of, minus the summation of x into the summation of y divided by the square root of n into the summation of x squared minus the summation of x squared. Okay, alright, times the square root of n into the summation of y squared minus the summation of y squared. Alright, so you need to know what is the y and what is the x. Okay, in this case our y is the dependent variable. Yeah, because y is a function of x. Y is the dependent variable and x is the independent variable. Alright, so for the area case, you're presented with that information. Property, that's property 1, property 2, property 3. Those are like our elements here. Yeah, these are like our elements. Element 1, we have the independent variable as 2 and the dependent variable as 2. Recall, we can just remind ourselves of the straight line. Y is equivalent to a plus bx. Yeah, meaning y depends. So that's why I'm telling you that y is the dependent variable. Yeah, and x is the independent variable. Alright, so you do this as per the formula and you substitute into the formula. I won't go into each of them. Yeah, but the key is knowing what you need in the formula. Right, together. That's why if we need the summation of xy, then we have to come up with the xy. Right, together. If you know you'll need the summation of x squared, actually this had to be the summation of y squared. Point of correction, let me just rectify something here. Yeah, this had to be, just to rectify something, this has to be the summation of y squared. Yeah, you have your y squared and then you sum them up. Yeah, at times we confuse the summation of y squared. Yeah, let me say it again. At times we confuse the summation of y squared. Here we are summing the y's we've squared. We confuse it with having the summation of y, whereby you first sum the y and then you square the answer. At times we confuse those two. Yeah, whereby like here the summation of y is 35 and then you square 35. Yeah, that's different from having the y's first squared and then you sum them up. You try out that number. You try out that number. You try it out. You try out the number. Okay, now let's go to regression. Yeah, regression analysis. So regressing is like going back. Yeah, it's like you predict backwards. Okay. Yeah, regression helps us to make predictions. Like if you have your x, the independent variable, you can be able to predict the dependent variable. You can make predictions using the regression. This is some of the historical note of how regressions came up. You can read about it. You can read about the statistical use of word regression dates back to Francis Galton. You can read about Francis Galton. Yeah, so he discovered that it could the relationship was such that you can read more about him. Let me not concentrate a lot on that. Purpose of regression. Yeah, regression analysis is used primarily to model causality and provide prediction. Causality, yeah, and provide predictions. We predict the values of a dependent response variable based on values of at least one independent variable. Under regression, we're going to talk about simple linear and then multiple regression. There's that regression whereby you have one independent variable, yeah, and one dependent variable, and then at times you have one dependent variable with several independent variables, which is the multiple regression. All right, yeah. So here you can predict the dependent variable, our y, in respect to one independent variable, one x, or several independent variables. Okay. Several independent variables. Yeah. So we are going to concentrate on understanding the simple regression and multiple regression. Alright. Simple regression is used to examine the relationship between one dependent and one independent variable. Okay, one dependent and one independent variable. Yeah, so after performing an analysis, the regression statistics can be used to predict the dependent variable when the dependent variable is known. So assuming you know your x, you can be able to predict the y. Okay, but it's for one dependent and one independent. Technically, it's the line that minimizes the square. You can read about the regression line. Yeah, let me just go where it is. Actually, it has to be somewhere. Yeah, it's far. I put it far. Okay, it's here. Let me talk about it. Let me summarize everything. This is our regression equation. Yeah, it's obtained from the equation of a straight line. Yeah, y equals to a plus bx plus e. Yeah, this is the regression equation. Y is equivalent to a plus bx plus e. Yeah, y is our dependent variable, and it depends on this. Okay, where a is a constant. Okay, so a is a constant. A is equivalent to what y will be even if x is 0. Okay, assuming we are looking at, let me propose something. Let me look at performance and attendance of class. Yeah, let me look at performance and attendance of class. Yeah, performance and attendance of class. Let me assume my y, the dependent variable, is performance. Performance in class. Let me call this to be performance. Yeah, let me call this to be performance. Our y is performance. Yeah, in start. Yeah, performance in start. Yeah, let me just call it in start. You'll be able to know that it's in start. Yeah, performance in start. That's our y. Our y is the performance in start. And then our x is let me just put this no. What are you doing here? This x, our x is in, let me give it a different color, the line. Let me call it, yeah, name it green. All right, our x is our x is attendance. Our x is attendance. Our x is attendance. All right. Y is performance. Okay. Y is performance in the study paper. X is the attendance. So we want to see, we want to predict someone's performance based on how the person attends classes. Yeah, so regression can help us on that. Yeah, regression can help us predict performance based on someone's attendance. Yeah, so I was saying Y is the dependent variable. In this case, is the performance. Yeah, which can be predicted based on attendance. The A is the alpha or the constant. It's equivalent to what performance will be even without attending class. Okay, meaning even if you don't attend class, there's some marks you can get, and that's our A, our constant. What you get even without the influence of the independent variable. The B is the coefficient of X. Yeah, so it shows us how much Y changes for each unit change in X. That's the B. Yeah, this is the coefficient of the X. It shows us how much Y will change for every unit change in X, how much performance will change for every unit change in attendance. Okay, and then E is the error term. Yeah, it's the error term. Okay, error term. There could be some other elements which may affect that relationship, and we'll capture all those in the error term. Okay, there's some things we may have left out which can predict the relationship, so we get up all those in the error term. There could be some things to do with the sampling. There could be sampling aspects which might have affected the results. We put all those in our error term. So this is the formula we use to predict our A and B. A is our coefficient, B is our, A is our slope. Yeah, A is so A is our constant, A is our constant, and B is our slope or our coefficient. So these are the formulas we use. If you have to get the constant and the slope, we use those formulas. We use those formulas. Summation of y into the summation of x squared minus summation of x into the summation of xy divided by n into the summation of x squared minus the summation of x squared, and that. Yeah, so A, recall, is our constant. What y will be even when x is 0. B is the coefficient, called the slope. It shows us how y changes with a unit change in x. Okay, so I won't go that through that again. I've talked about it. Yeah, A denotes the y-intercept. Talk about that. A intercepts the predicted value of y. Okay. All right, we have an example here. Okay, we want to look at glucose levels as our dependent variable, and then age as our independent variable, meaning the glucose levels depend on someone's age, and we have 6 elements or 6 individuals or 6 observations. All right, so here we want to make predictions of someone's glucose levels based on the age. Recall X is the independent variable and Y is the dependent variable. Okay, so in this case the glucose levels depend on someone's age, and we have 6 observations. For the first observation, the age is 43, the glucose level is 99. The second element, age is 21 and the glucose level is 65, and the third 25, 79, and so on and so forth. Like I told you, when it comes to these calculations, the issue is knowing your formula. If I know, if I'm to get the A, I need the summation of X and then the summation of X squared together. Then I have to look out for this information in the question. That's why I drew a table. So it's best done if you tabulate. You get your information, the table, and then you'll be able to look out for these aspects. Okay, so that's why I'm having the summation of X, Y, because I know I will need it somewhere, or I will need it summation somewhere. I have my X squared because I know I will need it somewhere in the formulas, or its summation in the formulas. Alright, so to get XY, we got 43 times 99, it gives us 4257. 43 squared gives us 1849. 99 squared gives us 9801. That's how we got these elements. To get on our second draw, if you get 21 times 65, you will get 1365. Okay, if you get X squared, if I square 21, I will get 441. If I get the 65 and I square it, I'll get 4225. That's how we get them. So after we sum them up. If I have the summation of age, if you add this entire age, you get this. That's the summation of Y. If you add this entire Y, you get that. Okay, and then if you sum up the XY, you'll get that. If you sum up the X squared, you'll get that. Okay, so after getting this information, now we substitute into our formulas. So from the table above here, we've just extracted the key elements, but recall you have to have in mind the formula for you make all those calculations based on the formula. Recall our sample size is 6 because we have 6 observations. We have 6 observations. 1, 2, 3, 4, 5, 6. Or we've collected data of X and Y on 6 elements. Okay, so we substitute. We substitute each and everything into our formulas. So if we substitute them, actually let me bring closer the formula. Someone might be wondering, someone might get confused. Okay, let me have this. Let me assume it will come here. Let me see. Let me try to bring the formula closer to remind us. Okay. Alright. So let me put it here. Let me see if it will fit. Okay, it will fit by force. It will fit by force. At least you can see it. This is the A and B. So we get this based on that. Okay, we get this based on that. The summation of Y is 240. The summation of Y is 2486. It's here. We put it here. This is the summation of Y. Okay, the summation of X squared. The summation of X squared. Our summation of X squared was 11409. We put it there. Minus the summation of X is 247 times the summation of XY, which is that 20,489. Okay, divided by N. Recall our N is 6. Into the summation of X squared. That minus the summation of X squared. The summation of X is 247. But now here we need to square that summation of X. That's how we got that. So if you compute all this, you end up with that, and finally our A will be 65.14. The same applies to the B. Still you substitute as per the formula. Yeah, and after we can insert our values into the equation. Our Y is equivalent to A. Our A was 65.14 plus the B, which is 0.38522x. Meaning, if you have this now, you can predict a Y, or you can predict the dependent variable if given any value of x. Altogether, at this level, you can now predict Y given any value of x. Alright, let me see if time allows for us to continue with the multiple regression. Okay, we still have 5 minutes. I can briefly talk about the multiple regression. Yeah, so multiple linear regression, also known as simply multiple regression. Yeah, this uses several independent variables to predict the outcome of a dependent variable. With linear or simple, continuing with a simple linear, we're having one dependent and one independent. But now with multiple regression, you can predict your dependent variables, but your independent variable, you can predict your dependent variable. When you have several independent variables, you can predict the performance given several aspects, whereby you can have attendance of class as one independent variable. You have eating, yeah, as another independent variable, because we all know that eating habits determine how you perform. If you don't eat lunch, or if you eat badly, your performance may be affected in one way or the other. So that can be another independent variable. The age, even age, you may find that age determines the performance of a student. Okay, so in that case, you will predict performance based on someone's age, eating habits, and then attendance of class. Yeah, for our earlier example, we were looking at glucose levels and age. You may find that glucose levels can be predicted by other variables besides age. So there we'll have glucose level with age as one independent variable, maybe exercise, height as the other independent variables, and then that becomes the multiple regression. Yes, so this is how we can have a multiple regression. Yeah, initially we were only stopping we're only stopping at the first, yeah, but now here with the multiple regression, yeah, it's a bit extensive. Y is our dependent variable as usual. X, the x ones, these x's are our independent variables, or our several explanatory variables. B naught remains our y-intercept, what y will be when all these are 0. Altogether, what y will be when all those are 0. The b, p, is the slope for each explanatory variable. And then we have the error term, yeah, which is very, very important to cater for those other aspects. Yeah, there could be due to sampling problems, the biasness which comes up, some things we may have left out, and so on and so forth. So that's a brief of our regression and correlation. Yeah, we'll have further lectures on these, practical lectures, etc. Alright, but this was just to introduce us to correlation and regression. Alright, thank you very much. Have a blessed day.